have this nice story, and and then we can check in about the data. So somewhere in here, we have the formation of nuclei. So this is extremely high temperatures, cooling as the universe expands. So it's cooling adiabatically, so the entropy is constant, but the temperature's dropping very quickly as the universe expands. And at some point, for example, you pass through this phase where instead of having quarks, they cool and they condense into hadrons, and then they condense into nuclei, and you can actually predict the primordial values of the different nuclear species, the abundances of the nuclear species, and that's been tested by looking out there in the universe, and so you really, you really believe what's going on, and at that level, thanks to that. And then later on, you have the transition from. So at early times, the universe is completely opaque because it's so dense, and it's expanding and cooling, and at some point it becomes transparent. And what that does is you can look deep into the universe and hit that edge of opaqueness because you're looking deep in time as you look deep in space. And that's called the surface of last scattering, and we observe the microwave background. So we send satellites into space and observe photons coming from that surface of last scattering. And we have detailed maps of those. If you've not seen a map of the cosmic microwave background, just Google it. It's this amazing detailed map that's mapping the entire surface of last scattering. What we see in that entire image is consistent with this. And then we go on and form galaxies and measure galaxy correlation functions and so on. So there's a lot of great cosmological data, and it all situates itself very easily in this narrative. Another question?
So you said there's great, you can start from those early initial conditions and not just formulas and integrate them or something and get the counter conditions.
Yeah.
But how does something like dark matter affect that? We don't even have a solid theory for what it is, let alone, it's fine to say we don't know how many nuclei of each type there are.
Right. So that's one of the things we don't know, but we model. We have models for what it. So then, right. So the critical view could be that we don't have a clue what we're talking about, and the optimistic view is that we use cosmology to constrain the nature of dark matter, and the truth is, both of those things are true, and so the thing is, with dark matter of a certain sort, then everything hangs together, and I guess in the case of dark matter, since the whole history of particle physics is adding particles as we go, adding one more to be the dark matter doesn't seem like a ridiculous thing, and so it's kind of culturally a comfortable place in physics to be. Yeah.
I have a question to you. You didn't define entropy, but just to make sure I understand what you probably mean. So in information theory, we usually look at the entropy of the total system, and I think that's why Charlie said it could be zero. Now, the way you're talking, I understand it more like you're looking at individual pieces, like small pieces of the universe, and say that if they are sufficiently mixed, they have a lot of entropy, and then the entropy of the total universe is kind of the sum of all these pieces. So you're kind of not taking into account correlations, because otherwise, correlations could never be measured in some way.
So these are just particle at temperature T, okay. Particles in equilibrium at temperature T. So whatever you have to say about a box of gas, you could say about this. And it might be in a microstate, but yes. And practically speaking, you still assign an entropy.
You're really talking about the entropy kind of subsystems and then the sum of those.
Yes.
Which makes sense.
Yes.
Just to make sure.
That's right.
That's probably the difference to what.
And the sense in which, by the way, so one of the things that confuses students of cosmology is that if this is an equilibrium, how on earth can the entropy be low and how can it go up? And the thing is that there's local equilibrium of the particles, but the metric degrees of freedom, which describe the space-time, are completely cold. They're not in equilibrium with the particles, and it's the structure formation, the gravitational collapse that sets in and starts bringing the metric into more complicated configurations. That's the way the entropy. That's the sense in which the entropy is low here and grows over there. Yeah.
So there's two, let's seems like slightly different senses to me, and I don't know if these are really compatible. So one of them is the metric becomes complicated.
Right.
I don't know, it has lots of structure formation, so there's lots of dips and this sort of thing in it. The other one is there's like a big horizon, and the horizon
Right.
has area, and that's associated with
Right.
NUP. Are those the same? Are those different?
Well,
Do you just add them together? And
Let me tell you how I tend to think about that. So if you have a box of gas and all the gas is in the corner, you let it go, it's going to work its way out into the box. And those different states along the way, it might be hard to define the entropy for those states. But it finally equilibrates, and then you can define the entropy. But the dynamics, I would say that fundamentally there's some attractor dynamics going on that's moving it in the box, and that's the most fundamental thing. And then labeling an entropy, it's great when you can do it, but it's sort of icing on the cake. And so I would say the fundamental thing that's happening here is that the metric's getting more complicated and exploring more of phase space. And then the places where you can define the entropy are the black holes. So those are the sort of, those are things that are equilibrated enough to name the entropy, but they're part of this overall process that's more general. And I know Jonathan has his hand up for a while.
Yeah, I mean, maybe in answer to Renato, I think it's worth saying that for both the black hole and for the cosmological horizon, the entropy is just derived through the second law. So you just know that it has a temperature, and then you just use the second law. So you have no,
Oh, you can see.
anything beyond that is just speculation, whether it even corresponds to microstates or anything. It's reasonable.
Yeah, there's been a little bit more done with the black holes, but not enough to really call it solid, I would say. I'm enjoying this, so keep asking questions.
can I imagine all this microscopic structure, kind of, or not microscopic, but just detailed structures, just sort of evaporating in the very distant universe? All the black holes evaporate, you reach kind of particle heat depth, and then.
Yeah, that's where we're headed in this picture. Adrian.
So I think I missed something crucial about the last picture. It linked inflation to the small dip and small dip to the big dip.
Optimistically. So
I was expecting it the other way around.
yes,
the first time.
that's right.
So why?
So what I'm saying is that if you want to say how great this is, you would need something like that to be happening. I'm not saying, and I've actually explored how you might do this, and it's pretty quirky, but it's, yeah, you should be confused by that. That in some sense I'm celebrating that sense of confusion by drawing that picture. Okay, so now I want to tell you, so I've been kind of presenting inflation in this kind of wary way, right? It's claimed this and that, but here it is increasingly fine-tuned. Let me tell you something that's just really cool about inflation that I think is related to tuning. It doesn't completely substitute for what you need from a meta picture, but it's a pretty great accomplishment. Now I'm going to show a plot of log of length scales, various length scales I'm going to put on here, and log of scale factor or time again. And the first thing I'm going to draw is something called the Hubble length. Actually looks very similar to the other plot. So this is the Hubble length. And this sort of tells us, I mean, in some sense, it's maybe the most important for this conversation. It's that it's equivalent to a time, the sort of light crossing time of the universe in one doubling of the expansion, roughly. But now I want to tell you, so we can follow different scales in the universe as they move with the cosmic expansion, and they do something like this. And here we are today, just at the onset of cosmological constant domination. And we find, so here we are, this is sort of a scale that defines the dynamics of cosmology. And all the scales we observe out in the cosmos today have started really small compared to the sort of dynamical scale of the universe. And the thing is, every physicist knows what to think about field theory modes that start very small compared to any relevant dynamical scale in the universe. And we know that those modes live in their ground state. And how do we know that? Well, field theory has proven itself as a description of elementary particles, of scattering processes, and so on. And the only way you can get the right answer is take the short wavelength modes in their ground state. You can't pass a field theory class without being willing to put the short wavelength modes of your field theory in the ground state. It's just what field theory is. That's how field theory has earned its place in physics, is by being a theory in which you know you've got to take the short wavelength modes of the field and put them each in their ground states. So down here, we have the quantum field theory ground state, or quantum field theory vacuum. And it's just something we believe. So we're over here, we're saying, oh, why are we in this state rather than some other state? It could be all the space, but somehow we're in these special states. When we go here, almost no one asks that question. You say, oh, it's a field theory on short distance scales. It's got to be in its ground state. And so this is what I just call free tuning. So you take the question of what is the state of the cosmos, and you pull it out of this thing that everybody believes, and you take the ground state of field theory and plaster it across the universe. And the remarkable thing is that it agrees beautifully with the data. So you can ask whether you're being critical enough by just embracing the quantum field theory vacuum, and I think that's a very interesting question, especially since nowadays we have, we think maybe space-time is an emergent phenomenon from something very different from space-time. We scrutinize this in the context of holography, in the context of the black hole firewall problem. We're sort of getting very curious about the exact nature of the quantum field theory vacuum. So I personally think it's very interesting to take a closer look at this, but what I tend to think is, wow, what an exciting thing. The quantum field theory vacuum is an interesting thing. Inflation is something that can take that vacuum and plaster it across the universe. So everything you observe through every possible telescope is telling you something about the quantum field theory vacuum. That's a pretty cool situation. And it is if tuning is explaining why you get one state rather than many other possibilities, what inflation does is it links you to the quantum field theory vacuum state. It links the state of the universe to the quantum field theory vacuum state. And I don't think it's a complete enough story to address all the kinds of questions you might have, but it's a really interesting thing to do for lots of reasons. So I want to leave my comments on inflation on that positive note. So it's a mixed bag. We won't really understand the full story until we have a meta theory that explains some more of this stuff. But in the meantime, we have this really great mechanism to pull a particular quantum state and plaster it across the universe. Yes?
So if I would imagine I prepared the universe in a non-vacuum state at the very beginning and inflation happened, inflation typically dilutes particles. And so what you would find is very quickly you don't have very much information about that initial state unless you populated it with particles of arbitrarily high momentum. It's the same thing as saying if you want to see initial conditions, you need inflation to last not that long. So it's typically quite hard to. So if inflation lasted long enough, it tends to erase things unless you populate the vacuum with particles of arbitrarily high momentum, and then you're completely determined to back into it when you started out.
So I agree with all that, and so you're narrow, you're sort of boxed in.
Yeah.
I happen to be, in fact, with Henry, I've written a paper on how there's holographic arguments that favor short inflation, and then with other co-authors have explored what kind of deviations from the perfect vacuum might be tolerated. Furthermore, inflation could start with a bubble or could start from some special thing. So So, but I think the gist of your point is that there's not a lot of wiggle room. I agree. But within that wiggle room, there's possibility of some really cool observational effects. So it's still very interesting. Yeah.
So-
Could someone help me get the screen down and the projector on? Yeah, go ahead with your question.
Yeah, I'm gonna see if I can say this sort of, as I understood it, more in elementary terms, and you can tell me if this is the right story or not. So we have a gas in a box, and all the gas molecules everywhere is some sort of the highest entropy state. And you can imagine a medium entropy state is something where they're confined to the left half, or somehow confined but not fully specified. And then say there is some sort of zero entropy state where all the particles sit in one corner. And we always, anytime we want to have an arrow of time, we always need low entropy initial conditions. So in that sense, we have tuning, but we say that this is okay from like a kind of philosophy of science perspective because we can describe that in like a small number of bits. Like from an algorithmic complexity standpoint, we can describe that initial condition small. So